Good morning, everybody. All right, let's give people another minute or two to join, and then we'll start. Yeah, I don't know what that's about, but oh well, the lighting is strange. And can everyone see my screen okay? All right. All right. Oh, attendance is even lower today. I guess everybody's watching watching the recordings, maybe, or maybe there's some other deadlines coming up. Election. That's the elections like several days ago are causing people to that's an interesting reason. All right. Well, I guess everybody is still glued to their computer waiting for the election results, apparently. Exams. Okay, exams make sense. Yeah, there's more people coming in. There's more people coming. Okay. All right, well, let me get started with some of the announcements and logistical stuff. So we are quickly approaching the end of the semester. This went pretty quickly for me. I don't know about you guys, but this felt like a very, very fast semester. Of course, it's not over yet, but we only have, what, 4, including today, 4 meetings left, including the final exam. I guess having it once a week also probably makes this feel faster. One thing is next Tuesday, I don't have office hours again. So it says except 11:10. Got another talk coming up. The last ones went pretty well. That hasn't been posted online yet, but I know some of you are interested in seeing it, so I'll try to post both of the talks on YouTube or something before the end of the semester if you're really, really interested in the research stuff I do. That's one thing. Also, for project 3, I made a couple of mistakes in the CodeGen .c template that I think I addressed these on Piazza. One was a missing header file, and one was the inputs to main, which shouldn't actually affect anything if you forget to include that in your template. But the header file will cause your program to not compile. I've updated both of these in codegen.c. So somebody's asking when it's due. So because of this, because of these little mistakes, but more importantly, because I never got to covering how to compile expressions, I pushed back the deadline for project 3 to now be another week later. I didn't push back project 4, but if a lot of people are also late on that, then I'll just push it back to the end of the semester. But that would mean there's no, that would just be the difference between 2 percentage points on project 4 being late. I'll probably push back project 4 as well. So just let me know if you feel that that's needed as well. Test cases for project 3, those should be coming up within the next week or so. Those should be coming up. I'll double check with the TAs about those. But we now have our implementation. We're also a little bit behind on making the implementation for that. But yeah, this the project 3 is pushed back a week because I also didn't give you the complete codegen.c, and also didn't cover in class how to do it, the expressions part. And I didn't push back project 4 yet, but likely push that back as well. I try to make the projects done before the exam period, so you're not trying to do a bunch of coding while doing your exams. But I also don't want you to lose points, even though it's just two percentage points, just because I'm behind on on the lectures. Okay, so today we're going to finish up the content on expressions from that I was behind on getting to last week. And then today we're going to talk about how pointers and arrays work in C and simple C, and how start covering how you actually will implement those in project 4. And then next week we'll try to wrap up all of the main lectures. If we don't get to finish that next time, I think we should be able to catch back up by next time. But the content today on pointers and the content next week on code generation should give you everything you need for project 4. Project 4 is implementing pointers and control flow constructs, if statements, while loops. So I've also made some simplifications of the language for this project. So the syntax supports multiple levels of pointers. In C, you can have pointers to pointers to pointers. You'll only have to support one level of indirection. I'll give you the code for doing typecasting, because we're not actually supporting multiple types in our simplified language. There's really nothing to do for typecasting. You literally just pass through the results to the parent. When there's types, you'd have to you may have to use some machine instructions to change the bit width of the data, and no need for arrays. So as we'll see today, arrays are really just in C at least, they're syntactic sugar for pointers, and we'll see today how that is. But I'll leave that as a bonus exercise for those who are motivated to try to do array allocation and implement the constructs for accessing arrays. But once you get how pointers work, doing arrays is much simpler. Okay, so I think Piazza is all caught up. The TAs have been really good about answering, and I've answered some questions as well, a bit to some degree. Any kind of lingering questions about, any lingering questions about project 3 so far? So today we're going to cover the rest of what you need for that, and the deadline is pushed back. But are there anyone kind of stuck on the code templates, getting their code to compile, or anyone still having issues? So fprintf is for standard error. So somebody asked about fprintf. We're not actually going to check fprintf at all. So you can use that for debugging output or error messages. So somebody asked about project 3, echo money sign question mark. So they asked, sometimes it doesn't give the ret val immediately. Anytime you run a program, it should, okay, so as long as you don't run another program after the program of interest. So if I'm running a.out, the money sign question mark will have the return value right away. But if you run anything else in the meantime, like I type ls, then the result, the echo money sign question mark will have the return value of the last program you've run. I don't know if that is your issue, but I'm not sure. Can you be more specific about not giving the return value immediately? You might also double check your assembly code, run it through GDB, and make sure. If you're getting different return values from the program, then your assembly code may not be setting EAX, the A register. So the return values are in the A register. And if there's any uninitialized variables or mistake in setting RAX. Okay, so if you're getting something, so if you're returning 0, you should get 0 every time. Double check that. Well, okay, I can actually show an example of this. So here's a program that just returns 1. This is going to be very funny if my program is broken as well, but hopefully it's not. So I'll let me compile this simple C program to simple C2.s, and we can see in the assembly code that it's moving the immediate value 1 into RAX, pushing RAX, and then popping RAX, pushing RAX onto the stack, and then popping that value into RAX from the stack. And when we compile this program, it gives me a.out by default. It should tell me the return value is 1 always. So double check that you are setting the RAX register at the end of your main. Yeah, it means that your expressions have to work properly, and I think return is implemented for you in main is implemented for you. So the return value should be being popped from whatever the expression code generator is providing, is setting the pushing onto the stack. And we'll cover expressions more today. That it could be just in the expression processing. Okay, yeah, and then so we'll cover expressions, and we'll go over. Yeah, I'll be going over using GDB today again as well, and I've added those instructions. They're in the project descriptions, and now they're also in the lecture from last week. So one thing that I forgot to do in Vagrant is automatically have GDB automatically installed, but it's very easy to use the package manager to install GDB. And then we'll walk through PEDA again. So if you remember from CDA, the state of your machine is the processor's registers, the memory, and where you are in the code, the instruction pointer or the program counter. And so the PDA, it gives a nice interface to show you all that state at the same time, including the stack. But I'll step through it again for the examples in class today, and hopefully, if you have any more questions about it, hopefully that will answer it. Just let me know when we go over that today. Okay, so let's get into it today. For So basically, the first thing we're going to do is for project 3, let's cover how to compile expressions. So expressions are subtle and a little bit tricky to get right. There's many techniques for compiling them. The technique I'm giving you is easy to generate code for. It won't necessarily generate the fastest code, but once you understand the kind of scheme for how expressions work in a compiler in Simple C, it should be much easier to generate code to do it. Let's first go to the whiteboard to figure out, to take a look at how this scheme works. It's very much like how type checking worked with expressions. So if you understand how the parser produces a syntax tree, this hierarchical structure that represents represents the order of operations in the expression and the nested expressions, and you understand how type checking does this post-order tree traversal to figure out the type, then that should make understanding how expression parsing works also a little bit easier. So first, let's go over how expressions work in a syntax tree. Recall that if we take a simple expression like, let's say, well, let's make this even simpler with constants. Let's say we have 2 plus 3, the expression 2 plus 3. Think about what's the syntax tree for 2 plus 3. In the tree I gave you, you would have a binary expression. Let me avoid my horrible, well, okay. My handwriting is not very good, but I will try my best. You'll have a binary expression node that will have 3 children. One will be an int expression, which will have the child 2. One will be an op. I forget the actual name. I think it's op. That will be a plus, or an I mean, strictly speaking, it'll be an enum value plus. And the third child of binary expression will be an int expression with the number 3. Questions on this? With type checking, the way it worked is we did a post-order traversal. So the goal of type checking was to do this post-order traversal that led to the root of the tree, or the root of the expression tree, to be annotated with the type of that expression. So we were inferring what the type would be by looking at all of the operands of expressions. And the way that worked is we would do this post-order traversal of the tree until we reach a leaf node. And when we reach a leaf node, we use our built-in definition of the language, like the fact that 2 is always an int type, 3 is always an int type, and plus has this type, this function type, where it takes 2 parameters of the same type and returns the same type, and use that to infer what the parent was. With, oops, sorry about that. Let me get my notes up again. Oh, it crashed. Okay, sorry about that. With expression generation, we do something similar. We traverse this tree in a bottom-up fashion, emitting assembly code as we go. And so the trick here is that we need to be able to write code generation for each node of this expression tree without having to know about what the parent looks like or what the other sibling looks like. We need to be able to emit assembly code that will just compose together in linear order and give us the right answer at runtime. So remember, we're not evaluating this tree. We're generating assembly code that will guarantee at runtime that the runtime assembly will compute the same thing. It's a translation rather than an interpretation of the code. And the little trick that we're going to use is we're going to provide a guarantee that each expression node provides to its parent that will allow the code for the parent to find where the value at runtime of this node is. It's almost like say merge sort, where you design the recursive function so that the return value has some guarantees to the caller of that function. So in merge sort, the return values of each merge function would guarantee that it has a sorted list for just that piece of the larger list. In this case, what we're going to do is we're going to guarantee that whenever we generate code for one of these nodes, that the resulting assembly code has the value of that expression as on the top of the stack. So somebody asks with that, oh, if you weren't given that guarantee, would you use look ahead to check the parents? So look ahead is a notion from parsing. So that just allows you to find the next token for parsing. But if we weren't given that guarantee, we'd have to have an algorithm that can process the whole tree and find some facts about that tree, like how many temporary variables do we need? Can we allocate space for that? Do we have enough registers that we can allocate the intermediate values of that expression to registers instead? So without that guarantee, we'd have to provide a guarantee about the entire expression tree or some fragment of the expression tree. So that's a little bit more complicated to do. The Dragon book also has an algorithm for finding the optimal number of registers needed for an expression tree. So it turns out that by taking advantage of the order in which the operations happen, you can use fewer registers overall. So the Dragon book has this, well, I can't remember the name of the algorithm, but the Dragon book has an algorithm for this. Hopefully it's in the readings I gave you, but if you're interested, let me know and I'll point to you in the Dragon book where it is. But yeah, that makes the algorithm more complicated because we have to reason about a whole subtree. In this case, the algorithm I'm giving you will allow you to just reason about just the individual nodes of the tree, but the invariant that it provides, the guarantee that it provides, is very subtle in the way it behaves at runtime. So let me go through an example of how the assembly code will be generated from just this simple example. And then we'll see why this works out at runtime. So remember, we're not actually evaluating the tree. We're generating assembly code that is guaranteed to evaluate the expression in the right way at runtime. And making sure that these guarantees work out is really the main trick in writing compilers. Okay, so the guarantee that I'm going to provide is whenever we generate code for each of these expression tree nodes, we generate a push instruction that will save its value onto the top of the stack. For this particular example, what we get is roughly, for integers, we move the immediate value into a register. I'll just pick RAX here. And then that's all we need to do to evaluate, generate code for the number 2. And our main guarantee that we provide is that we generate a push instruction that puts that value, the value that is computed at runtime of that leaf node onto the stack. So when I say push RAX at runtime, that takes whatever the value of RAX is and pushes it on top of the stack. With me so far on this? I do the same thing for 3. So remember, we do this in a post-order fashion, post-order traversal. I do the same thing for the number 3 expression. So I move the number 3 into RAX, and notice that I'm using the same register here, and we'll see why that's okay. And again, push the guarantee that every expression provides is that the top of the stack at the end of evaluating the code, running the code for that expression, the top of the stack will have the resulting value. So again, I push RAX. Now, here's the trick. In binary expression, what we do is we first recursively call, because remember, we're doing this in the bottom-up traversal. So the very first thing we do in binary expression is just recursively generate the code for the left and right children. That means we call CodeGen expression on the left child and the right child. That's the first thing we do. Now notice all of these code generation functions are void functions. They don't return anything during compilation. They just guarantee that a certain segment of code is generated in the order in which you call the code generation functions. So we call the code generation functions here, and that will, in bottom-up fashion, traverse the 2 child nodes first. And then, because this is post-order, after we traverse the children and generate code for the children, then we generate code for the plus operation. And the way we generate code for that is, let me get the actual assembly instructions so I don't mess this up. Let me look at my notes for what the real instructions look like. We generate an add instruction. Oh no, I'm sorry. The first thing we do is we get the okay. So at runtime, the code that we generated for the children will now guarantee that the 2 values are on the top of the stack. So what we do in the binary expression is we generate 2 pop instructions. I need to give myself more space here to do this. We generate 2 pop instructions. So I'm just going to pick 2 registers to put this in. The order, of course, does matter, first in, first out. Oh, tree traverse. So somebody said, who knew tree traversals actually had to use? Tree traversals are like bread and butter of language processing and lots and lots of algorithms. If you understand, and also if you understand tree traversals, you can understand recursion. Okay, so we generate 2 pop instructions because we called code generation for 2 children, and because of our invariant says that the code generated by any expression will, as the last thing it does, call a push to push that value onto the top of the stack. So the first thing we do in binary expression is we recursively call those code generation functions, and then we generate 2 pop instructions, which at runtime will pop those values from the stack into registers so that we can operate on them. Okay, so now we have, at runtime, we generated code that has both the values of the children, no matter what they are. We don't care what the children are. We just care that the code generation function ensured that it emitted a push instruction with the value. We generate 2 pop instructions. Note that our BX because this is FIFO, this is first in, I'm sorry, Philo, first in, I can't remember this. The last thing you push is the top of the stack. And so because we generate the code for the right expression first, the pop instruction will put the value of the right operand into RBX, and we pop the value of the left operand into RAX. So somebody asked, don't we push binary expression? We're getting there. We're getting there. So now we've generated code that ensures that at runtime, we have the values of the two operands in two registers, RBX and RAX. Then we can actually generate the add instruction. And now this, you have to, I mean, I always have to sit and look at the reference manual and just make sure this works out. The add instruction in AT&T syntax has the, well, let me just write it first and then I'll explain it, why it is this way. So confusingly, this is the, and I'm making this even more confusing because I wrote the wrong thing. This is the left operand and the destination operand. This is the right operand. So this says, take whatever's in RAX, add RBX to it, and save the result in RAX. For add instruction, add is commutative, so it actually doesn't matter the order. But for subtraction and division, this matters, the order matters. So recall that in AT&T style syntax, the last operand is the destination and it's the left operand. So somebody's asking, before the entirety of this add operation, should the RAX be saved onto the stack and then pop back into RAX after the, I think what you're saying is right. I think that's, so let me show the output of this compiler, and then we'll see why this works at runtime. Okay, so we've recursively generated the code for the two left and right operands. We don't care how the code is generated because we've, as the programmer, have written a guarantee that says every expression will push the resulting value. We'll generate a push instruction that pushes the resulting value onto the stack. We pop those, we generate instructions to pop those two values, and now we can, into registers, and now we can generate an add instruction. And finally, to ensure that our invariant, well, is held so that we can compose all of these recursion functions together, we finally generate a push instruction that will store the resulting value onto the stack. So somebody's asking, they're confused about why we pop RBX. Wouldn't the register be empty? So push, the meaning of push is to take whatever the value of the register that you're pushing and store it in memory onto the stack. Pop is the opposite. It reads that value and puts it into the register from memory and then decrements the stack pointer. So that is push moves the value of RAX into memory. It's basically a kind of store operation. And pop reads the value of memory and into a register. So it's a kind of load instruction. Makes sense so far? Okay, that's good. So this is where this, so if you, okay, so over time, if you practice these kind of recursive techniques, they, for some problems, actually become easier to write, because the way you do it is you just define an invariant. That just means you define some guarantee that every recursive function that you're writing provides. In merge sort, that guarantee is that whatever merge sort does, no matter how you do it, it's guaranteed to give you a sorted list as its return value, or as its whatever its invariant is, whatever its output is. And then in order to make sure that all the recursion works together, you write the recursive functions assuming that when you make that recursive call, that it will provide that guarantee. And so you don't think about all of the confusing chain of recursive calls that it has. Instead, you say, well, let me just define ahead of time what guarantees that this recursive function should have, and then write the recursive function assuming that those guarantees are already met by any functions you call. You just pretend that the functions are already written and pretend that it provides those guarantees, so that when you write one recursive function, you don't have to think about how all the other ones work. You just make the assumption. And when you write the function, you just provide that guarantee when writing the function. So in this case, without writing any of the other expressions, we can write binary expression and just provide the guarantee. So we use the guarantee here. So even without writing int expression or other expressions, we make the assumption that CodeGen provides this guarantee. We just make that assumption. We can write this without even writing the other ones. I mean, of course, the program won't run yet, but for binary expression, we can actually get it right by just making the assumption that any expression, recursive expression compiler, code generation function, provides the guarantee. And then we make sure that we, the binary expression, also provide this guarantee to other functions. If you go out and become like a professional software engineer, this kind of, even outside of recursion, this kind of notion of invariance and providing guarantees, or sometimes they're called contracts or interfaces, this is really the bread and butter of writing large-scale software. The only reason that you can, say, call printf and actually reuse all of this functionality to print something to the screen is because the library writers for printf provided a bunch of guarantees to that API. So they're guaranteeing that however it's written, whatever system you're on, there may be different implementations of printf and the underlying system. They provide guarantees to you, the user of that library, that ensure that if you call this in the way that we define, you will get the expected behavior. It's almost like a contract or a guarantee. In the same way that you have an electrical outlet in your wall, as long as you build an electrical product that has the right support for the right voltage and the right AC versus DC and the right prong shape, you can just plug right into that interface and use it without worrying about how it's implemented. This is really the key of these. This is this function abstraction that I talked about in the very beginning of class. Functions are one way, one very basic fundamental way to provide these guarantees, provide these interface guarantees between components of your software. And this is what allows us to create really, really large software and reuse libraries and other components. With recursion, this is a very clever way to design an algorithm at the, in a very detailed way by exploiting these kinds of guarantees between recursive functions. But if you could understand this notion of interfaces between functions and the guarantees that they provide in terms of their input and output, then you can write recursive functions much more easily without having to reason about like multiple calls to many functions. Instead, you try to think about how will one function written correctly ensure that the entire recursive algorithm works correctly. So that's why I say that if you can tackle this, if you can tackle this challenging problem, it will make other software engineering problems much, much easier, because you're not going to have this very, very complicated recursive reasoning in most algorithms that you're working on. And when you encounter new algorithms, you can use a recursive problem-solving approach to actually make the amount of code that you write smaller and actually a little bit easier to write. So if you work out ahead of time what these guarantees should be, and the whole trick will then be, well, what are the right guarantees for this recursive function that'll ensure that the whole algorithm works? That's the hard part. If you can work that out, then coding it will actually be simpler and may even be safer to write. It might be easier to get the program right. So somebody's asking, is recursion faster than loops in C? So generally speaking, no, because of the overhead of calling functions. Whenever you do do a function call, there's a little bit more work you have to do. You have to push stuff onto the stack, which is a memory operation. But to make recursion fast, in many cases, there's a very common optimization called tail call optimization. If you've got, I think I mentioned this a couple weeks ago, if you've got a recursive algorithm where the very last thing it does is make a recursive call, it turns out that because functions are not actually supported by the architecture, instead it implements them using the stack and branching. If you've got a recursive function where there's only one recursive call and it's the last thing in the function that you do, if you look at the assembly code, it's actually equivalent to just a loop, what the behavior of a loop would be. Well, we haven't looked at how loops are compiled, but really it's just an unconditional branch back to the top of the loop. And you'll see that a function call looks very, very similar to this when you generate a recursive function call that only has a single recursive call at the end of the function. So generally speaking, recursion is not faster on our hardware because of the extra memory operations involved in functions. But compilers have all sorts of clever techniques. In addition to tail call optimization, they can inline functions. So if they can guarantee that you don't need those memory optimizations, then they can just literally cut and paste the contents of the function at the call site instead of having to do a call. So somebody's asking another interesting question. So we can see that we can take loops and turn them into recursive function calls with tail call recursion. But somebody's asking the converse. Can you take any recursive function and turn it into a loop? So this is an interesting one. So I'll ask you, the listeners, is this possible? Here's a strong statement. For any recursive algorithm, can you also implement this using a loop, using, say, a while loop instead? So what do you guys think? Is this always possible, or are there maybe cases? Okay. So somebody got very good. So okay. So for some of you, you've probably learned this before, that any recursion can be converted into an iterative version, but how? So some of you pointed out the key to this. If you have a stack, you can do this. So I don't know if in CS1, when they talked about tree traversal or graph traversal algorithms, you can use a queue or a stack to implement it, or you can use recursion to implement it. You can have equivalent functions to do this. And notice that how do we implement? So somebody thought it might have been impossible. Okay, yeah, so it's possible with a stack. So you can just Google the stack-based algorithm for tree traversal. But to really draw the connection here between compilers and how programming languages are implemented, how do we implement function calls in Simple C? How do we implement that in assembly? The content we went over the past couple of weeks. How do we make functions in our programming language? How do we implement them in Intel assembly? What's the key to implementing them? So we do branching, but what's the key to implementing functions in Simple C? Or how do we do it? How do we implement functions in C or Simple C? Oh, silence. Yeah, stack frame. Stack frame is the key. We use a stack to do it. So behind the scenes, the compiler, for any recursive algorithm you're doing, the compiler is actually generating stack instructions to push and pop from the stack to generate assembly code that will implement that recursion. So it's almost like an automated, it is an automated translation from functional style, where you allow a recursion and you can specify your algorithm using functional style, but the compiler will translate that to a kind of iterative version where it's using the stack to do that iteration, to do that iterative method. Because the hardware does not truly support algorithms in functional style. It only supports branching. And so the compiler generates stack instructions to implement functions, but the byproduct of that is that what the compiler generates is a kind of iterative version of any algorithm you write. So functions as we conceive of them in programming languages, where the state is frozen, waiting for a callee to come back to the caller, that's not possible without holding that state somewhere in the machine. I mean, it's not possible in the physical machine without having a stack to do it. So the compiler is the functions in programming languages are not really physically realizable without translating them to the instructions that our machine supports. Now, mathematically, we can specify any algorithm that we can specify on a state machine. We can also specify using a functional style. And so there's famous work by, so Turing did the famous foundational work on modeling computation using state transition machines, like state machines. And his, actually, I think it was actually his advisor at some point, Alonzo Church, defined computation using this functional style, using the lambda calculus. And you see some hints of this with lambda functions in Python or other languages, anonymous functions. So somebody's asking, can you simulate functions in assembly with gotos and jumps? So I suspect that you haven't done project 3 yet. When you do project 3, you'll see that the way you implement functions is exactly that. You use, well, okay, yeah. So yeah, it is with gotos and jumps, but they're hidden. So yeah, even if you saw the way we generated with Intel assembly, they're hidden a little bit in the call and return function instructions that Intel has. The actual implementation of call and return in Intel is really just unconditional branches. All the function call is in the Intel side is unconditional branches. It's just gotos. They do a little helper work for you to set up the stack frame, but you could certainly do that stack frame setup yourself and then just use an unconditional branch. Intel is a CISC architecture. It provides these more high-level assembly instructions that combine several low-level operations for you. But functions, the way our compiler simulates functions in assembly is literally by just emitting unconditional branches and setting up the state to ensure that we can return to our function without blowing away the state of that function. Okay, so hopefully this is all coming together a little bit, and why compilers really reveal some fundamental aspects of computer science, this distinction between different models of computation. So even with C being a low-level language, this notion of functions is a different model of computation where you have this frozen state that you can return to and recursively call, and how this functional notion of computation is distinct from the state machine notion that is physically realized or closer to being physically realized with, say, an Intel instruction set and the actual architecture implementation of that instruction set. And it also shows how you can automatically convert between the two. So while you could hand convert a tree traversal algorithm written in a recursive function style to an iterative one using a stack, a programming language will, in effect, in some sense, do this conversion automatically between these different models of computation. All right, that was a big aside. How did we get? Oh yeah, we got there by talking about this distinction between recursive definitions of tree traversals versus iterative definitions of tree traversals. Okay, so back to the code generation. What makes this, as everything in compilers, what makes this really hard to reason about is we have to forget how we interpret this expression, because we all know we could write an algorithm to interpret this binary tree. You may have even done this in CS1 where you write an expression interpreter. But we're not interpreting it, we're generating code, assembly code, that will do the interpretation at runtime. And we have to provide these guarantees at compile time to ensure that the input language, the behavior of that input language, has the same behavior as the generated assembly code when we eventually run that generated assembly code. We're not running this expression, we're generating code that will be guaranteed to have the same result when it is run at and when that assembly file is assembled and run at runtime. All right, makes sense so far? So that, when we talked about this toy compiler in the beginning, we're generating assembly code. We're literally just printing out assembly instructions. Okay, so let's kind of run this compiler and see what the output instructions will look like. So recall that this is a post-order traversal of the tree. So when we call our code generator on the binary expression, and the first thing it does is it recursively calls the code generation on the two children, the left and right children. Okay, so what will happen first is the left child gets generated. So here's our assembly output. The left child gets generated, and then the right child gets generated, right? So we recursively call the left child, recursively call the code generator on the right child. This is so far the resulting assembly code that we output in linear order. With me so far on this? So we've finished recursively generated code for the left and right children. Now we're back in our parent, the binary expression. The first thing it does is it generates pop instructions. Those pop instructions, whoops. The first thing it does is generate pop instructions. So those get generated right after the code we generated for the two children. And then finally, we generate the add instruction. Let me just do the add instruction first. No. We generate this add instruction. Sorry about that. I killed push. Then we generate the add instruction. And finally, I should have just moved this over at the same time, but we generate the push instruction as the last thing we do in binary expression. Does that make sense so far? So this is what will happen if we see the output of actually run this code generation function. Even though we're doing this post-order tree traversal, we're emitting the assembly code line by line into a linear order, just a linear output of assembly code. So somebody asks, is this all generated by calling CodeGen expression? Yeah, so CodeGen expression, just like in the type checker, will dispatch to the correct CodeGen expression according to the kind of AST node it is. So that's all handled for you. So all you have to do is just call CodeGen expression, and the dispatch will send it to the right CodeGen expression function. And as long as you've ensured the guarantees on each of your CodeGen expressions individually, once you do this post-order traversal, the output assembly code should just work. It should just, because we've worked out these guarantees ahead of time, the output assembly code should just work exactly the way we want. So just to highlight this a little bit more, here is the left child, here's the right child, and here is the binary expression. This is, well, actually, that's the left child and that's the right child. This is the entire binary expression. So the tree structure is kind of reflected in the code. You can actually infer it from the code. Even though the assembly is in linear order, you can kind of reverse engineer. If you know how the compiler was written, you can look at the assembly code and almost reverse engineer what the original tree looked like. And in fact, this is how decompilation tools work. So NSA famously released Ghidra. IDA-Pro is another popular commercial tool. These can look at compiled code and actually infer what the original programming language looked like, what the original program looked like in source code to some degree, because the compiler generates code in this schematic style. For various reasons, it can't exactly recover the original source code, but it can actually do a pretty good job of inferring what the original source code might have looked like. So somebody's asking, should we have moves and pushes in binary expression before our pop calls? So no, you don't need to have moves and pushes before the pop. The very first thing you do is recursively call the code generations functions for the children. So it's the child functions that handle the moves and pushes for you. So this code is handled by the child function. We just call it in the binary expression. Again, but yeah, both of these is handled by the child functions. We just call them. What we do in binary expression is, after we recursively call those code generators, we emit pop instructions to ensure that at runtime we can recover those values of the expressions into registers so that we can then do our binary operation. And the very last thing we do in every expression function is emit a push instruction, because that is what provides the link, the guarantee, or the invariant, whatever you want to call it, the contract between all of these code generation functions. And that's the beauty of recursive recursive function composition. And I mean, any function composition can work this way, where you provide guarantees that each function provides and that each function depends on when it calls that function. So the very last thing we do is emit a push instruction. So if you're having problems in your code, make sure that every expression emits a push instruction with the right register that holds the result of the expression at runtime. Make sure it has that push at the end of it. All right. Okay. So somebody's asking, why does RBX happen here if in our children we both use RAX? So okay, so another kind of hidden invariant here, which is not obvious from what I said, but we can infer it from it, is that between each of these code snippets, we have no guarantees about what's in the contents of registers. What makes this algorithm easier to generate code for is that we can make the assumption that the registers hold nothing. We make no assumptions about what's inside of registers. So when we are in the binary expression code generator, we make no assumptions about the values inside of registers. And instead, we are allowed to blow away and do anything we want with those registers. When we're in here, what pop does is it blows away the contents of RBX and populates it with whatever was on the stack. So similarly, when we emit this code, we provide no guarantees about the contents of RAX. So does that answer your question yet? This is getting to it, but are you starting to see so here, so to bring this to fully answer your question, we certainly use RAX during the lifetime of this expression. We use RAX, but then we immediately store RAX into memory on the stack so that we no longer have to rely on that register holding the value at runtime. It always comes back to the stack, for this algorithm. So there are very sophisticated compiler algorithms that will maximize the usage of registers, but for our purposes, to allow for arbitrary, so there are a finite number of registers. So you can write expressions that have 100 intermediate values that we could never have enough registers on any, for every machine. You can always find a machine where you can make more intermediate values than there are registers, and you'll always have to push to memory. For this algorithm, we just pessimistically always push to memory, always save the value in memory, so that we don't need to manage different registers for different expressions. So even though we're using the register, we're allowing our generated code to use the register for the lifetime of that expression, and then always at the end of that expression storing that value onto the stack. So someone asked, at the expense of speed? Yes, at a big expense of speed. So if we you might even start noticing that there is absolutely no reason in this particular snippet of code, there's absolutely no reason to push these values to memory. The reason we do it, though, is that if we needed to know that this should move the value to RBX, our compiler would have to communicate that information between calls to the expression, to CodeGen expression. This design that I've given you makes it so that the agreement between these code generation functions is very, very simple. Otherwise, we'd have to say pass which register. So the binary expression could say, I would like you to store this result in RBX. But once we have a recursive set of function calls, a recursive set of expressions, we're going to quickly run out of registers and have to anyway at some point store register values to memory, and coordinating that across the entire expression tree is much more complicated. And so even though this code is extremely not optimal, so you're gonna notice like here, there's a push and a pop from RAX without any change to RAX in between. So there's absolutely no reason you could totally optimize away this push and pop. And there are actually simpler compiler algorithms that will go and look at non-optimal assembly code and look a couple instructions at a time and say, well, okay, I can remove this little push and pop. But yeah, we don't have to do that in this class. This is just a very, very simple compiler. If you're interested in that, I'm happy to point you to some resources for looking at that. There's also like graduate courses or other courses online you can see to learn more about that. But yeah, so this is totally at the expense of speed. The trade-off is simplicity of writing the compiler, so that we can finish this, by the end of the semester, and you'll still hopefully get the main point here and all the kind of rich, interesting ideas that we have, fundamental computer science ideas that we have in representing languages. Yeah, so somebody's asking about the register allocation. So do you more or less check if you're out of registers? So effectively, yeah. So the thing is, we can't check at runtime. So the compiler needs to basically predict ahead of time how many registers it's going to need for a certain set of operations. For one particular expression, that's not hard to do. There are optimal algorithms for doing this. But once we have branching, where the code may take different paths and use different registers, then it becomes much harder to provide these kinds of guarantees because we have to account for the fact that the code may take several paths during runtime. Then we quickly run out of registers. So there are kind of near optimal algorithms, or there are optimal algorithms for doing it that are much slower. And so I think most compilers today use kind of faster compilation algorithms. So we have to consider both the time it takes to compute the optimal set of registers, which slows down compilation, and trade that off with how well the code will perform at runtime. So LLVM, for instance, there's a good blog post by the creator of the LLVM compiler where they talk about some new register allocation algorithms that they use in LLVM. If you're interested in seeing that, remind me in Piazza, and I'll send a link to that blog post. But he goes over, he's an expert in compiler writing, and he goes over some of these engineering trade-offs in register allocation. But yeah, basically, we as the compiler writer need to know ahead of time how many registers we have and try to find a optimal or near optimal use of those registers to avoid memory operations. For a lot of optimization in the compiler, the whole name of the game is avoiding memory access because it's so much slower than register operations. So there's all kinds of tricks for avoiding, just geared around avoiding memory access, including inlining functions, not doing the actual function call, but copying the contents of the function at the call site, duplicating the function instead of actually updating the stack frame and making the function call. Register allocation and register allocation optimization. Okay, so here is our resulting assembly code for our expression. Questions on this so far? Okay, so I'll leave it as a little exercise to you to see what happens, or actually I'll actually just show it. So, but I'll leave it as an exercise to you to work out yourself. What happens when we have nested expressions? So if instead of a binary expression, instead of a single binary expression, I had some nested expression like this, will this algorithm work? Well, so first of all, will this algorithm work out? If I've got a nested expression like this, what's going to happen with our compiler? Is this going to work out with the invariants that we selected? Any kind of thoughts on this? This is kind of taking to the next step of how this compilation works. So somebody's guessing that yes, it'll work. So I think it will work. And the reason it'll work is because even if we have these nested expressions, each of the generated code for each of these expressions will push to its parent. Yeah, exactly. The stack is doing the heavy lifting, as one of your fellow students points out. So even though this binary expression does not care what this binary expression does with registers, does with the stack, it doesn't care as long as the top element on the stack is the value here. So we're just going to see the exact same code that we saw for this child expression. Effectively, we're going to see this nested inside a larger binary expression. That's what we'll see. But instead of doing this by hand, let me show you this in my implementation of the simple C compiler. And then let's use GDB to walk through and see why this actually works. So keep this notion of this recursive invariance, or invariance between functions, to make this kind of recursive algorithm work at runtime. All right, yeah. So we got a few minutes before the break. So let's take a look at some examples here. Okay, so this has a whole lot of stuff in it. Let's take a simpler example. My imaginatively named simple 3. So let's start with our let's just return the value. Okay, so here's our simple C program. Let's compile it. Here's the output. So in the examples I've given you, I've emitted comments as well to show you where what each piece of the code generation functions are doing. So let's go through this. Let's go through this real quickly. So all this stuff at the beginning is the stack frame setup code. Recall from our. Let me try to tie this to our tree here. So recall that we had our when we evaluated the integer expression for 2, we just moved it into a register and pushed it. We see that code here. We do the same thing for the 3 integer. We see that code here. And then we see the pop instructions here. So now, once we're here, this was generated once we're back in the parent binary expression. We have the addition being emitted and the push So here's the addition being emitted and the push. So here's the exact code being emitted that we did by hand on our whiteboard here. Everybody see that? Now, if we look at, say, if we look at the return function, so I've implemented return for you. Notice that what it does is it recursive. So, okay, so now we're in, so I'm going to give you some context here. So we are in the code generator for main. And I'll leave it to you to look at the output of and follow the comments to see, where we are in the trace of the code generation function. But the one of the last things we do is generate the return expression, return statement. So the return statement is really just an expression. We generate code for that expression. In this case, it's our 2 + 3 expression. And then in order to save that into the return value, so the function ABI requires the result of the function, the return value, to be stored in RAX. So all we have to do to consume the result of that expression is pop it from the stack, right? Because the expression guarantee of all those code generation functions is that the very last thing it does is pushes the value onto the stack. So whenever we have a user of an expression, any other statement that uses an expression as its child AST node, all we have to do is emit a pop instruction that puts it into a register for us. In this case, we can just pop it directly into RAX because that's according to the function ABI, that's where we need it in order to have the return value. Making sense? So this is what a lot of your code will look like in statements and expressions if they have child expressions. You're going to pop the value from the expression into some register. And remember, our code generation functions are providing no guarantees about what's inside of registers. So each of our code generation functions is free to use the registers however we please. In this case, for functions, and you have to implement this for your function ABI as well, the return value of the function needs to be in RAX per the Intel ABI. Yeah. All right, questions so far on this? So in the last couple of minutes before our break, let me walk through GDB. So that way we can actually see what's happening, why this works at runtime. And get a little review of how to use GDB and this PEDA template or settings for style for GDB. So somebody asked, are we going to get a fully working version of Project 2 for Project 3? I think you should already have this available. If you look at the Project 3 instructions, this should be available to you here. So we use the same, you're going to have to do the same rigmarole that you did for Project 1 for Project 2, but hopefully you've worked out the kinks in doing that. No, it's okay. It's okay. It's a good question. Yeah, you'll have Project 2 implemented for you. All right, let me, before we go to break, let me save this assembly code. So here's our assembly code. I will compile it. Actually, let me bring this up here. So here is our compiled function. Let me know if you want this bigger. I wanted to put all this on the screen, but let me know if you'd like to see this bigger, and I'll enlarge the size. Okay, so I compiled our output assembly code. And if I run it and look at the output, what should we get for our return value? Should be 5, and indeed we get 5 as our return value through the Intel ABI and the Unix standard that main will return to the exit code of the program. So now let's take a look at GDB. Recall that I've put instructions for GDB both in the lecture notes from last time and also in Project 3's description. So all you got to do is follow these instructions, make sure GDB is installed on your Vagrant machine, call GDB on the program. So I do this, so by default, PEDA is using the Intel syntax, so you can, you can there's a file you can update to make this always use AT&T, but you can also just run this set instruction. Okay, so the first thing that we do in order to be able to step through our program is we set a breakpoint on main. So B is short for breakpoint. Run the program will start running, and then it'll basically just stop and wait at the beginning of main. And then we can use the step instruction feature to be able to step through each assembly instruction. So that, you know, I gave a link to the GDB manual, I think, or you can just Google it. It has a ton of functionality. I am no expert on GDB, so you can like step into functions versus step over functions. You can step through assembly, you can step through C instructions. So I'm just giving you like the very basics that I kind of worked out to be able to step through each instruction of a simple C assembly program. Okay, so I have to zoom out a little bit here. Let me know if this is too small, and I can make this bigger. But in order to see all of the pieces that PEDA shows to you by default every time you step through an instruction, it gives you the state of all of the registers currently on the machine. It gives you the current program counter or instruction pointer in our code segment. So you can see here, this little arrow is basically the instruction pointer. It's the same value that we see here in the state of the instruction pointer. So the instruction pointer register holds the current instruction or the next instruction that we're going to run. I think it's the next instruction, right? And we see all the surrounding assembly code. So it takes a little bit of matching, but if you look at our compiler output, now I can't even see it. You can see that it's showing this point in our compiled output. So it's a little confusing because the decompiled assembly here is showing the values in hex, whereas here our values are in decimal. So don't that might throw you off a little bit, but just realize that you know, if you have a 0x prefix, that's the hex value versus what our simple C compiler, which is the decimal. I mean, you can certainly omit hex if you like from your compiler, but just be aware of that little gotcha. Okay, so that's the register state, the current instruction pointer, and the surrounding disassembled assembly code. And then finally, we have the state of the stack. Now, as we talked about last time, what's confusing here is that it's showing the top of the stack first, even though in memory, the top of the stack is at a lower address. So this is the top of the stack, and this is the offset from the top of the stack, which is actually going higher in memory addresses, but it's conceptually, in terms of the stack abstract data type, it's lower in the stack or towards the bottom of the stack. Does that make sense? So this is the current top of the stack. So it's kind of flipped with respect to the way we view it in memory, where the high memory address is the bottom of the stack, the low memory address is the top of the stack. So a couple of little gotchas when you're reading this disassembled output and the state of the machine using PEDA. Questions so far on this? Okay, I think everybody's got it, I hope, or you're just totally fading and need a break. So I hope everybody gets this, gets what GDB and PEDA, what his output looks like. So let me just quickly step through our expression so you can see how the machine state gets updated at runtime, and then we'll take a break. So let me just quickly step through to get to the beginning of our expression. So recall that this is evaluating the integer expression 2. So all it does is move 2 into RAX. So now notice here that RAX now has the value 2. And the next thing it does is it pushes RAX onto the stack. So here on the stack, here is the new value onto the stack. It pushed it onto the top of the stack, now has the integer 2 on it. The next snippet of code that we generated was the integer expression for 3. And same thing. So somebody's asking, they're confused why GDB is better for debugging than just looking at the machine code. Yeah, that's really up to you. So if you're comfortable just debugging the assembly output, by all means. If you are confused, so GDB is more for debugging. So if you output the wrong code and you're not sure why, it might be helpful to you. Instead of tracing by hand, it might be helpful. It's really up to you. Yeah, it's really up to you. I mean, it's definitely good to be able to, in your head or on paper, trace the state of the machine. You should definitely be able to do that. GDB is not a crutch for not being able to do that. It's just a tool. If you already are able to do that, it's a tool that helps you automate that process. So yeah, all debugging tools, don't view them as a way to do debugging for you. View them as a tool that helps you when you already understand how to debug, helps you automate some of the debugging process. So that's actually kind of a good question. This is actually why in the past I haven't, pushed so hard on using GDB or recommended using it, because you should be able to debug yourself and view these tracing and profiling tools as automation for your ability to your ability to debug. These are just automation tools for helping. Yeah, GDB can also help you debug C programs. So if you compile with -G, it'll leave the some information in the assembled program that'll actually allow you to trace through the source code with GDB. So yeah, just Google GDB on debugging C code, and you'll find resources or Stack Overflow questions on that. Okay, so back to our program, we have the generated code for the integer expression. So we move 3 into RAX. So notice RAX now has the value 3. Our state still has 2 on the top of the stack. And then when we run the push instruction, now our stack now has 3 at the very top. Our right operand is at the top of the stack, and it has 2 right after it. So now we're back inside the code that we generated for the binary expression. It recursively called the 2 children expressions. It does not care what those expressions were. It does not care whether it was an int expression, another binary expression, a unary expression. Doesn't care. All it cares is that the last instructions pushed the values onto the top of the stack. So the first thing binary expression does is it pops the top of the stack into BX. So notice 3 is now gone from the top of the stack, and our BX has 3 in it. Don't worry about the fact that IX also has 3 in it. Don't worry about it. We're making no assumptions about what the registers are. And then the next instruction we do is we pop RAX. We pop the left operand. And so notice that now RAX and RBX have the left and right operands respectively. And the stack is now back to the same state it was before we started processing those 2 child nodes. So somebody's asking, the numbers to the left are incrementing by 8 because that's what we use as our offset. I'm not sure which numbers you're talking. Oh, the number, yeah. So that's because the state, the entries in the stack are 64 bits wide, the quad word or whatever it's called. They're 64-bit wide. So the offsets into the stack are by 8. And that's actually the same reason why when we look up variables and retrieve variables, that we use an offset of 8 into the stack. Okay, so now here's the state of our machine. We've recursively processed, or we've processed the instructions for the left and right children. We've popped them off the stack and put them into registers here. And then finally, we can do our simple single add instruction. The add instruction stores the result, per the Intel instruction set design, stores the result in the A register. So now the A register has 5. And the very last thing that the binary expression does is it pushes that resulting value onto the stack. Now our stack is updated to have 5 in it. And at this point, we're back in main, the generated code for main. And as I was mentioning before this, what main needs to do is it needs to save the resulting, the result of the expression into RAX. So what it does is it pops the value of the stack into RAX. And so now RAX has 5 in it. Of course, it had it there before, but we're not worrying about optimizing the compiler. It pops that into RAX and finally, runs the epilogue of the function and ends. And so, our return value is going to be 5, and we're done. Okay, questions about this? All right, I think we definitely need a break at this point. All right, I'm glad this makes sense. So hopefully this is another tutorial on using GDB. So again, all of these debugging tools, I would strongly recommend tracing by hand first. And once you get the hang of that, so as somebody else mentioned, why use GDB? So GDB will not debug for you. It's called a debugger, but it does not debug for you. GDB automates the sum of the tasks you need in order to debug. Debugging is done by you, the programmer. There are automated ways to do debugging, which we will talk about a tiny bit at the end of the class. Actually, this is kind of in my area of research that some techniques that I'm very interested in. So I'll give you a little summary of that, of how you can do automated debugging. But GDB does not automate debugging for you. It automates some of the tedious tasks that you need to do in debugging, like tracking the state of registers, tracking the stack. But to use a debugger effectively, you should already be able to do that by hand in long form on paper and even potentially in your mind. So really good assembly programmers, which I'm not a good assembly programmer, can have a mental model of the machine in their head that includes the register state and the stack. They'll be able to do that in your head. For novice assembly programmers like you and me, just write this by hand. Write out the state of the stack by hand if you need to trace through the assembly. And the bigger challenge is tracing through the compiler behavior and distinguish between the runtime behavior assembly and the behavior of the compiler to output that. So somebody's asking, do I think that's imposter syndrome? Yeah, maybe. I think imposter syndrome is, it's for some people like me, it's, kind of hard to get over. Well, okay. So I don't know if that's necessarily imposter syndrome. For me, that's just a realism about what my skills are. I'm not an expert in assembly programmer. And also, I think it's good to distinguish between imposter syndrome, being realistic about your skills, and also giving yourself a high standard to achieve to. So just because you're not at that standard yet, or not, you're getting there, doesn't mean you're an imposter. It means you have these, you have these goals and standards that you want to achieve, and you're working at them. And there's no reason to let any, I'll not use an expletive. So let any people who are putting you down make you feel like an imposter, because that's on them for doing that. There's really no reason to someone who is, trying to achieve a certain standard, get to that point. Now, if you don't have that standard at all, and you're just willing to, not at all care about whether you want to achieve that standard, that's a different thing. That's not imposter syndrome. That's just, you don't care. But yeah, and you're all students. You're all taking class. So there's no reason to feel like an imposter. And I'm just being realistic about my, I would love to be an expert in assembly program and reverse engineering. I'm not, it's not my area. I have other expertise that I work on. It's also very hard to become a real expert in any area, much less like just one area to become an extreme expert in. That's very, very hard to do, given all of the needs of life. We need to work, we need to make money, we need to survive. It's very hard to take the time to become an expert in everything, much less one particular area. But one thing that I hope to convey, I didn't really make this explicit, but to at least have the kind of stem of knowledge, so that if you need to pursue an area, that you'll have the independence and self-motivation to be able to do that with confidence and without fear, and with the knowledge that you can do that you can take the right independent steps to find that knowledge, to seek out either the right experts to do that, or to have the right mindset for, it's almost like debugging, have the right mindset for where do you need to improve, rather than convincing yourself that you're already an expert. Instead of doing that, think, well, what am I missing? What do I need to, what's the next steps of knowledge that I need in order to become an expert, or have enough knowledge to do whatever task I'm trying to do. Anyway, so let's take a so what do you guys want? Is a 5-minute break enough, or should we do a 10-minute break? I'm fine with either, because I went over past our, so five is okay. Is 5 okay with everyone? Does everyone want? Okay, so let's do a 5-minute break. Let's come back at 11:36 according to my clock. Somebody said they might fall asleep if they do 10 minutes. All right, so let's do 5 minutes. Let's come back at 11:36. And I'll take a break as well. So see you in 5. I was peeking on camera to check the time, as you guys noticed. Somebody's asking about ident expression. They said it'll be covered in class. So here's, if you're, it was covered in class, I think, but here it is just in case. Okay, I think we're back. That's 5 minutes. You guys are real warriors for, it's a lot of content to go through. And we're actually back up to the norm of number of participants. It's actually pretty good. We have almost, well, a little under half of everyone in class, maybe a third actually. All right, so that's expressions. So that should give you all of the information you need, more or less, to implement code generation. So just make sure you have your ast.h reference, take a look at the code generation rules, watch, I went over, fairly quickly through the expression stuff. You can just watch through the recording and pause as needed. Try to do this stuff by hand, work out the assembly code by hand, use the debugger if needed. So let's move on to the content for project 4. So for project 4 is going to have implement pointers and also implement control flow statements, if and while. So first we're going to look at pointers, and I've got some slides for pointers and arrays. All right. So as I hope you know from CS1, you at least, I think, know that pointers hold memory addresses. They're just like any other value, like an integer value or a floating point. They hold memory addresses. What's really confusing and what you may not know is how they're actually implemented behind the scenes. And pointers are probably one of the most confusing and also one of the parts that leads to software bugs and serious vulnerabilities in C. It's one of the more confusing parts of C and working through it. And so if you had trouble reasoning about pointers, hopefully understanding how they're actually compiled and what they do at the assembly level will hopefully make it a little bit easier to understand them. But yeah, so pointers hold memory addresses. And it turns out that memory addresses at the assembly level are also basically integer values, or at least there's no way to distinguish between the representation of integers and addresses. In the same way that we saw in the type checking lecture, there's no real distinction at the assembly level between floating point numbers and integers. They're all just bits in a register. And it's all about how we use those bits. That's what makes them a different type. And so somebody already pointed out that that's why you can do some address plus one. You can do pointer arithmetic. And C explicitly allows this kind of pointer arithmetic. But even though from the machine representation point of view, it's all just bits, what makes a pointer is that it's used with different operations in the same way that an integer and a floating point number are distinct because we use different machine instructions to operate on that data. So let's take a look at some of the simple C constructs for dealing with pointers, and they're basically just a copy of C's pointer constructs. So there's a couple things we can do in our C language. We can get the memory address of a variable using ampersand. So I think all of you may have seen this, but may not have used it very much. But if you put an ampersand before a variable name, what you'll get is not the value of the variable, but you'll get the memory address of that variable. Okay, so here's our program. We declare an integer x, and we declare a pointer to an integer y. We assign 10 to the variable x, and we assign ampersand x to the pointer variable y. So the question is, what's the value of y here? We know the value of x is 10. What's the value of y? Address of x. Yeah, good. Yeah, exactly right. It gets the address of x. And let's assume that this is inside of a function. Now that you have seen how functions are implemented in C, very good. So somebody already pointed out base pointer -8. Exactly. It's going to be some address that's within the stack frame, some offset, which is an offset from the base pointer. Very good. Very good. All right. So questions on this? Questions on this? Or somebody's asking, oh wait, would it be just be base pointer? It's okay. Don't worry about that. We'll get to the specifics of that in the code generation. The base, if you remember, if you go back and look at the Intel ABI and that web page, the base pointer points at the stack frame entry that holds the old base pointer. So it would be an offset of, actually it would be an offset of -16 because integer x is there first. Don't worry about the details of that, but just that's good. You're aware that it's an offset from the base pointer and it's some entry in the stack frame. But I'll provide the instructions for Project 4 already has how to actually compute that. So don't worry about the actual offset. Questions on this? Questions on getting the address of a variable? So if you've ever wondered in C what that ampersand means or how it works or why it works the way it does, is now that you know that all of these local variables are really just stored in a stack frame in memory, when you call ampersand, at least for a stack allocated variable, when you say ampersand, it's really just giving you that address in the stack frame. Pretty cool, right? That's all it does. Okay, so if there's no questions on that so far, let's move on to dereferencing a pointer. So there's two ways to dereference a pointer in C. You can either dereference it to get its value, or you can dereference the pointer and assign the dereferenced pointer a value. Let's look at what it means to dereference a pointer to get its contents. So the syntax of this is to put a star before an expression. In this case, we just put a star before a variable access. And it gets not the address itself. So y now has the address of x, but it gets the value of the memory that the pointer points to. So what is the value of star y here in this case? 10. Good. So to walk through this one more time, we have two variables. X is an integer, y is a pointer to an integer. We set x to 10. And so we now know from how functions are implemented that now a stack entry has the bits for 10 in it. We set y to the address of x. So now the stack frame for y has an address, which is actually an offset from the base pointer. And then when we dereference y, we look at the address that is stored for y in the stack frame, and then we go to that address. That address happens to be another entry in the stack frame, and get the contents of that address, which is 10. Questions on this so far? Questions? So hopefully this is some amount of review that you've seen pointers in C before. So this part, I didn't understand the question. This part's, So somebody's saying, oh yeah, we'll look at assigning to dereference pointers on the next slide. But somebody had a question. So this part, yeah, no, you'll be implementing this. You'll be implementing pointers in CodeGen yourself. So that'll really drive home how pointers work at the machine code level when you actually have to implement a compiler for it. So other questions on dereferencing a pointer to get its value? Okay, so let's look at how we can update the address that a pointer points to. So in the kind of like compiler lingo, the stuff on the left side of an assignment is called an L value. So L values are values that can resolve to memory addresses. So X, in the compiler at least, can resolve to some kind of memory address. That's the offset from the base pointer. And a dereferenced pointer, if it's a pointer, can also resolve to a memory address. That's in contrast to the R values, which are on the right-hand side of an assignment. So if you ever see that lingo in reading about compilers or languages, that's all it means: L value versus R value, left value versus right value. Okay, so when we have a pointer on the left side of an assignment, how does this work? So just like before, we assign X to 10. We assign Y to the address of X. And now we assign the dereference of Y to 11. So here's some, and then return the value of X. So here's some questions. What is the value of star Y? Good, star Y is 11, or at least by the end of the program, star Y is 11. What about here? What is the value of star Y? If before this assignment, what is the value of star Y? 10, good. Oh, so somebody said an address, so star Y, what is the value of star Y? Dereference of Y. So this answer, so for whoever answered that, what is the value of Y during this program? Good, yeah, it's an address. It's gonna be the address of X, which is in the stack frame. And then here is the main trick. What is the value of X when it's being returned? So somebody, yeah, 11, good, it's 11. So why is it 11? Good, yeah, very good. So Y, yeah, so you're all very good answers. Y is an alias of X. No, very good, very good. So Y is an alias. Y holds the address of X, all very good, exactly right. And so Y holds the value of X, and when we assign to the dereference of Y, the dereference L value, then this updates the memory that Y points to, which also happens to be the memory address that X is bound to. Good, okay. So I think everyone's, or at least everyone answering, has a good sense of how pointers work from the programming language semantics point of view. So let's take a look at how this actually gets implemented at the machine code level, because at the end of the day, just like functions, pointers are not actually, pointers are not really, there's no instruction that's like, here's a pointer. Instead, there are special instructions in Intel that allow you to work with memory addresses and store and load values from memory addresses. And so let's take a look at that. So the key to this is called memory indirect addressing. So normally, when we have a move instruction between registers, in the AT&T syntax, we take whatever the value, the move instruction means take whatever the value is that is in the RAX register and move it to overwrite whatever the value in the RBX register is, right? Everybody with me on this? Normal move instruction. With memory indirect addressing, AT&T syntax has a little bit of a very terse notation for it, but with memory indirect addressing, instead of moving between registers, yeah, so this notation we saw with the base pointer, this notation says, instead of moving the contents of RAX, it says move whatever the contents of the memory address that is in RAX, move that contents into RBX. So because this kind of holding memory addresses in registers is so common, the Intel architecture and other architectures just build in operations for doing this kind of memory indirect addressing. So normally you would have to call a load and load that into figure out pass this RAX as the address for the load it into a register, and then move that register into RBX. With the Intel architecture and other like CISC architectures, actually other even RISC architectures might do this as well. No, I'm not sure. But in a single operation, we can move the contents of memory that's given in a register. So instead of having to have a fixed address, we can have an address that's stored in a register, and then move the contents of this address in a single instruction, at least in a single assembly instruction, into another register. Make sense with me so far on this? So this is exactly how we implement, or more or less, this is how we implement this pointer dereference. So when we have a memory address that's on the right side, an R value, and we dereference it, this is the machine code that we use to implement that. All right, let's take a look at how when we have a pointer dereference as the L value, the left-hand side of an assignment. We just do the reverse. So if we have a memory address stored in the RBX register, we can use memory indirect addressing to move a value to that memory address. So this move instruction takes whatever the value, the contents of RAX is, and it moves it to the memory address that RBX contains. And so this notion of memory indirect addressing, this is where pointers come from. Pointers are just a register that holds a memory address or another memory location, memory contents that holds an address. And so we can even take this a step further by having pointers to pointers, where we follow the chain of memory addresses to get to a value. So I won't go over that too much here, but I'll leave that to you as an exercise to think about how does a pointer to a pointer get implemented, or a pointer to a pointer to a pointer. And you can do this, however much indirection you want. C may have a hard limit on it, but conceptually, you can have a pointer to a pointer to a pointer. And this is effectively how a linked list works. A linked list is, at least dynamically, it's a pointer to a memory location that has another pointer for the next location, and that next location has a pointer to another memory address. That memory address contains another link in the another list element, and it itself has a memory address. But for this class, we're just going to do single level pointers. Okay, so moving to a memory address using this memory indirect addressing is how we handle pointer dereferences as L values, the left-hand side of an assignment. All right, with me so far on this? Does this kind of lift the veil on what pointers are at the machine level? So somebody pointed out that it's another version of star, but it's actually a little bit more fundamental than this. Star is really another version of memory indirect addressing, because star it's made up. It's a programming language invention. In order to actually have a program behave the way we want with pointers, we translate it to assembly instructions that use this memory indirect addressing. Okay, so let's use GDB to walk through how this memory indirect addressing works. Okay, somebody has a question here. For this example, would RAX contain 10 and RBX contain the address to Y? Oh, so let me show an example of GDB, and hopefully that will make that clear. I didn't show the actual I was just showing examples for little snippets. So somebody's asking, does that work the same way with arrays? And so in C, that's exactly right. So arrays, I'll show this a little later in the slides. Okay, so actually, since people are asking about arrays, let me skip ahead to pointer arithmetic. So you guys already pointed out pointer arithmetic. So let me go over this now, and then we'll go over the code and how to actually compile this stuff. Okay, so recall that pointers are just memory addresses, and they look no different from integers to the machine. And so the machine is not going to stop you if you try to use arithmetic operations on memory addresses, because memory addresses are just integers. They're just integer representations. They're just bits in registers. So there's nothing stopping you, the assembly programmer, from getting an address, say getting the RBP pointer, getting the address, and then doing arithmetic on it. So here's a little bit of a tricky example here. So somebody's asking a question: do we ever use RCX or RDX? So for the way I recommend designing the compiler, we only use like 1 or 2 registers. We don't have to use those registers. A real compiler will take full advantage of all the registers for performance reasons. But yeah, there's no reason to use other registers in this compiler project. Okay, so let's look at a little bit more of a tricky example. This is a very, very tricky example where we use pointer arithmetic to dereference some arbitrary place in memory. So let me go through this code. We declare 2 integers, x and y. So recall that these get allocated by the compiler as stack entries. And then we have a pointer to an integer z, which also gets allocated an entry on the stack. We assign the x variable to 1, updating its stack entry. We assign the y variable to 2, updating its stack entry. And then we assign the z variable to be the memory address of x minus 8. So in Super C, the way I designed the type checker, for better or worse, was that it won't allow you to do a subtraction between 2 different types. So we do a typecast to force the compiler to allow us to use 8 as a pointer value. And then we dereference z. So the question is, what is the value that z, what is the dereferenced value of z? Okay, so somebody answers. Okay, so we got some good answers here. So good answer by one of your fellow students. So y in Simple C is allocated 8 bytes after x, as the student says, which is exactly right, because this is the way our stack frame is laid out. The stack grows downwards in memory. That is, it subtracts addresses in order to get new stack entries. So if we take the address of x, which has some entry in the stack frame, and we subtract 8 from that, we're going to get 1 stack frame lower in memory, which actually happens to be, at least in our compiler, happens to be the stack frame entry for y. And so as another student points out, the return value is going to be the number 2. So this is a very tricky example. So this is an extension of the tricky example we had before, where we have an alias to x, and if we dereference the alias, we get 1. But through pointer arithmetic, we can actually access any memory we want. Literally any memory we want, we can access, modify, and read the value of it using pointers. And in this case, we very cleverly went to used pointer arithmetic to start aliasing the y address in memory. Even though we never explicitly got the address of y, we used pointer arithmetic to move around the stack frame, look around the stack frame to get the value of y. And now we have an alias to y. And if we modify z through a dereference, we're actually going to start modifying the value of y as well. With me on this one? You guys follow along? Questions on this? Pretty cool, right? So this is why pointer arithmetic is powerful in a sense, in that it gives you basically a very similar machine model that you have when writing assembly. You can just access arbitrary memory. But this is also why it creates serious, it's a lot of power. You can really feel the bits with C and pointers. But it also creates lots and lots of security holes and lots of problems if you can do arithmetic. It also makes it very hard to guarantee that the program is working the way you expect. So somebody asks, are you 100% sure that it will be in the right order? So for our compiler, because we're writing the compiler in this way, we can guarantee that this will happen. But if the programming language, like I think C doesn't provide any guarantees about, well, actually, I'm not sure if the C standard itself guarantees that the stack frame will be in this order. I suspect no. So doing pointer arithmetic to access local variables in the stack frame, I think would be undefined behavior in C. I don't think it would be guaranteed by C. So if it works in one compiler, it may not work in another compiler the way you expect. I think that's the case. I'll have to double check. Let me know if anybody knows whether I'm wrong or not. But I think that accessing local variables via stack frame offsets is not part of the C standard. Actually, I'm pretty sure that's the case. So this would work depending on the compiler. So anything so remember we talked about undefined behavior, which is like a catch-all for behavior that the compiler is not responsible for, but may actually compile and allow you to use. That will not guarantee that program will behave the same way across different compilers and across different architectures as well. So yeah, actually, if this is compiled for this definitely will not work across different architectures because the integer, because the stack frame size might be different. The size of integers may be different depending on your architecture. So this is not portable code. This is undefined behavior. And yeah, C does give you virtually unlimited power, which is with pointers, which is why a lot of security exploits are due to this kind of pointer behavior in C. So somebody asked if compilers use random offsets for security reasons. I'm not aware if they use random offsets to avoid accessing stack frames, but there are some mitigations to stack overflows, which we'll actually look at in a couple of weeks. I'll go over a stack smashing attack. But there are some techniques where you put a random known value, a nonce, in the stack so that you can detect whether some program has manipulated its stack, whether the stack has been overwritten through some unexpected input to the program. And then you can check that when you return, before you return from a function to halt the program and check for a security violation. I don't know if I'm not aware if compilers will use random offsets. I think some compilers may they can eliminate the use of variables altogether and avoid having to have a stack frame for it. I think you can do that. I think for local variables, you can certainly do that. You can avoid even creating memory for it at all if you can guarantee that you only need to hold that variable in a register. All right, other questions on this? So this is a very, very subtle example that really illustrates what pointers are doing behind the scenes. And so I find that trying to think about pointers from the programming language point of view is pretty hard to do. It's much easier to think, well, this is a memory address, and this is doing memory indirect addressing when I'm dereferencing it. For me, that's a way, way easier way to think about pointers. Just forget about the C language abstraction and just think what happens in memory when you do this. So somebody's asking, why would I need to cast 8 to a pointer type? So this is just because the arbitrary design I had of the type checker. So if you remember, the type checker will reject a program where you have a binary operation between two different types. And so, yeah, that's why. In C will not reject this. The C type checker will, I think, actually I have to double check this, but I think the C type checker It may just provide a warning depending on which compiler you're using or which, how pedantic you want the warnings to be. C will allow, so C is designed to allow pointer arithmetic. It explicitly allows it for doing like lower level system stuff. It allows pointer arithmetic. And so it's not going to complain. I don't think it'll complain if you do pointer arithmetic, depending on your warning level. So some compilers, because it's such a, for lots of application programming, using pointer arithmetic is probably like not needed. So different compilers will allow you to give different warning levels to warn you whether you're doing pointer arithmetic like accidentally or something. But so in simple C, I specified the type checker to reject programs that use different types in the operands for an operation. So the type casting is just basically a way to subvert that explicitly. So it's basically saying, I'm the developer, I know what I'm doing, I really do want to do this cast. And so the language is going to be like, okay, you told me you want to do the cast, it's on you now. It's on you now for that. So that's why there's a cast in simple C for this. Okay, so knowing pointer arithmetic, how pointer arithmetic works. Now let's see how arrays work in simple C. So it turns out that in C, arrays are really just pointers. So if you declare an array, or even a string for that matter, which is really just a character array, behind the scenes, C is just saying, hey, now I've got a pointer. So that symbol, like if X is a pointer to a character, then X is treated behind the scenes pretty much exactly like a pointer. And yes, exactly right. So somebody says pointer to the first element. So yeah, we say an array is a pointer to the first element, but a pointer to the first element and a pointer is no different. There's no difference between a pointer to the first element and a pointer, because C and C does not track how long that pointer is. So there's absolutely no information held at runtime that says this is a pointer to a 5-element array versus this is just a pointer to a character. And so that information about sizes of arrays is effectively lost in the assembly code because it's just a pointer. And so when we say pointer to a first element, that really just has to do with how we access elements in that array. So somebody asked, an array is like a linked list that's consecutive in memory behind the scenes. Sort of. Arrays and linked lists are two ways to specify the abstract list type. But a linked list is yeah, I mean, from the abstract point of view, where you just have an ordered set of elements and you can access them by their index. In that sense, linked lists and arrays are the same. But their structure and memory are completely different. So an array is just, in C, the array variable is just a pointer. And it's up to you, the developer, to make sure that you're using array indexing correctly. So yeah, so exactly right. So somebody's asking, this is why it's easy to go out of bounds and not get errors in C. So you'll go out of bounds in C and not get a compile time error, but you may get errors at runtime. You may get strange untrapped errors. So if you remember when we talked about type checking, we made this distinction between trapped errors and untrapped errors. C's arrays will not stop the compilation if you make a memory an array access that is out of bounds of the memory. So somebody mentions that arrays are contiguous in memory, so just like the stack frame, each element is in one memory location after another. Linked lists are different. Linked lists, as I discussed, are structures that are in separate places in memory that have pointers to point to the next element of the list. Yeah, so somebody points out also, very good point, a linked list holds the reference to the next item, whereas an array relies on pointer arithmetic to access the next item. Couldn't have said it better myself. That's exactly right. So an array, the reason that an array is different is that exactly right. It uses pointer arithmetic in order to find the next elements of the array. Linked lists have an explicit memory address via a pointer in each linked list node structure. Okay, you know this system landscape. Great, great, excellent. Okay, and so if we look at how this is actually implemented in the compiler, the array declaration itself is basically just declaring an array. If you declare a fixed size array, then the compiler will just allocate that enough memory on the stack for those array entries. Right, so somebody's already pointing out if you don't malloc an array, so you can either have the compiler allocate space for an array for you by having a local variable that's not not declared to be a pointer, or you can use malloc to allocate a chunk of memory and then access that memory just like an array. Use the array indexing to access that memory. So it's a little tricky in C because you have to allocate memory that is the number of entries times the size of the type. And so one common idiom in C is to say, size of array times the size of built-in function and then the type. So size of is a kind of built-in aspect of C that will take a type name and give you or a variable name and give you the size of that in bytes, the size of that variable. So I don't want to go too much into that in this class. Hopefully you saw that in CS1 or CS2 using malloc. But from the point of view of array indexing, there is no distinction. Array indexing only has a pointer to the first element. That is, it only has a pointer. And it's up to the developer to decide how that should be allocated, whether they want to allow the compiler to allocate it on the stack versus explicitly call malloc. And when you call malloc, you're just malloc just returns a pointer. It doesn't return an array, it just returns a pointer. So it's up to you, the developer, to make sure that you're using array indices in bounds. There's no language enforcement of that. To drive that home even more, this array index doesn't do anything more behind the scenes, at least in C, doesn't do anything more behind the scenes than simply pointer arithmetic. So if you look at the generated code, you'll see the same code that you'd have as if you did pointer arithmetic, roughly. Okay, so what does array index look like? What is it? It's syntactic sugar for pointer arithmetic. What does that look like? It takes A, because remember, A is just a pointer, and it takes the index that we've given in our syntax, and it multiplies the index by the size of the type that we're pointing to. So if A is a pointer to integers, and integers are 8 bytes wide, then an index into A is going to be 8 times the index 2. That value added to the pointer A. A holds a memory address. Doesn't matter whether it's a pointer to an array or a pointer to a single scalar. It's just a memory address. And this array index just takes an offset from that memory address. So somebody's asking if it were a double array, it would be 2 times 16. It depends on the architecture. So I think in C on a 64-bit architecture, integers are actually 32-bit. In Simple C, I made everything 64-bit per actually Josh's good suggestion to avoid having to do any bit width manipulation and type dealing with types. But on a 64-bit architecture, a C integer, I think, is 32 bits, so 4 bytes wide. And then a long, it would be the 64-bit version. For floating point, I think floating point is a 32-bit floating point, and then double is 64-bit. So you can Google this to confirm this. And I think in modern instantiations of C, there are types for like 128-bit floating point. but I am not super familiar with that. But in short, one also portability issue that C has is that the types are architecture dependent. So if you go back and you program for some 8-bit architecture or some 16-bit architecture, the bit width of ints on that machine are going to be different than the bit widths of ints on a 64-bit machine. So that's also one nasty portability issue with C, particularly when you're doing pointer arithmetic. C allays some of that by having the size of functionality where you can just give the variable or the type and the compiler will just give you the right bit width using that. But if you're hard coding bit widths in your C code, you are eliminating portability. Just like in my tricky, where was it? My tricky pointer arithmetic example, where I assumed the compiler had an offset of 8, I created non-portable code. In the same way, if you start hard coding bit widths or make any assumptions about bit widths related to types in C code, you're going to remove portability. Now, historically, like for instance, in systems programming, developers will conditionally define type defs like int32, depending on what architecture they're on. So it gets, yeah, I mean, I deal with this a lot in my research because I work with like the preprocessor and variability aware processing. But if you look at some of these header files or system code, actually, I might as well show you some of this. Let's see if I can find this. Yeah, okay. So the standard library now actually includes some of this stuff. I think the standard library does. Yeah, here we go. So the standard library, I think the C standard now includes support for these type definitions. So let's see if we can find something here. So you'll see that, well, okay, we actually have to look for, this is getting a little bit into the weeds of C's standard, the C standard for defining types. Here we go. So here is where we see a 32-bit, like the, so this is making a new type called 32-bit int. So that if we're the user of C, we can write portable code that guarantees that variable that we declare has a 32-bit type. But the problem is the C standard itself doesn't provide any guarantees about the width. Instead, you'll have a system-dependent header that depends on which architecture your system supports. So if you have a 32-bit operating system, this header file will instead of defining 32-bit ints to be int, it will use long for 32-bit ints. And we see here that for a 16-bit int, this type def will use a short, which is defined to be half the width of an int. And so depending on your architecture, that will either be 16-bit on a 64-bit architecture, or will be 8 bits on a 32-bit architecture. So anyway, going into the weeds a little bit about these differences in systems and historical portability issues with C. I hope that was a little bit interesting and not too much of a tangent, but let me know if do you have any questions on this, or is this interesting at all to any of you? This is very much nuts and bolts of like C and systems, that kind of legacy stuff that we're still living with today. Okay, questions on this? Or have I just totally lost you with some of this very, very nitty gritty of C, of the C language? Oh, but anyway, to sort of pop the stack a little bit. Yeah, so basically C, this is really the interplay between the definition of the language and the actual machine. So C historically has been very much a machine-dependent language, like mostly portable, but has these kind of system-dependent attributes to it. And then the designers of the language have kind of overcome this through kind of clever definitions of headers. Okay, so I'm really glad to hear someone says this lecture made pointers make more sense. I'm really, really glad of that. That is one of my main goals in this lecture. So, even for me, instead of trying to reason about pointers from the programming language level, I find it much easier to just sort of break the abstraction and think, well, this is just memory addresses, and these are just memory indirect addressing that's going on here. And so if you're just aware that this register now holds a memory address, and when I go to read and write to it, I'm just, instead of reading and writing to that, moving to that register, all I'm doing is moving to the address that register holds. And then I would take a look at, try thinking about double pointers or triple pointers just to see that. Yeah, so somebody says they get scared when they see pointers since they barely write C. So yeah, I can understand that. So I mean, one of the main like hallmarks of modern programming languages is avoiding the need to manually worry about pointers. So being able to use pointers is essential for programming. To be able to like create structures at runtime in memory, you have to use malloc. I mean, you have to request from the operating system new memory, and you don't want to have to fix ahead of time what all your data structures are going to be. So we want to be able to use malloc to access and create new memory allocations at runtime. But we also don't want to have to like think about pointers explicitly themselves. So modern languages like C++, which has new and delete and uses the the RAII standard for trying to safely use memory, and Java, which completely hides pointers from you and treats everything is basically a reference in Java, and they use clever unboxing and boxing for scalar types as needed. That's kind of the story of like modern programming languages over since several decades ago. It's just avoiding having to worry about pointers. But even today, if you look at like system code is still written in C. And so you still have these issues with pointers, but in the last couple of decades, a couple of languages, 3 languages mainly, Rust, Go, and Swift, have emerged to try to take over the systems programming world without sacrificing the kind of performance and virtual machine needs that Java has and other high-level languages have. So we'll see how that pans out. All 3 languages are, they're being used to some degree. Mozilla is using Mozilla is using Rust for some of its system software and browser. Google is championing Go, and Apple has designed Swift. Yeah, so there's also Rust is really cool. It's based on a lot of very cool academic work to ensure security in the programming language. So there was an older language called Cyclone, an academic language that came out of academia that helped ensure safety of memory safety without having to do explicit pointer stuff. But a little dig on Rust that I heard at a conference a couple months ago is that Rust is a language that everyone hears is really awesome and likes, but doesn't actually use, unfortunately. So I'm in that camp, and I was like, oh man, yeah, I'm in that camp where I think it's really, really cool, but I haven't actually like done any extensive programming in it. Hopefully that'll change because it is a really cool language. But Go and Swift are also other attempts. They all have kind of different approaches to handling memory management. Rust uses the compiler, which is why I like it so much. It uses program analysis in the compiler to provide guarantees about memory usage and do garbage collection effectively automatically. Go uses garbage collection without having a separate garbage collector. Go has a separate garbage collector at runtime that cleans up memory for you. And Swift uses reference counting, so that when you do memory accesses, it increments a counter, and when that counter goes to 0, you can now know that the memory isn't being accessed anymore. So Swift has an issue with when you have circular memory accesses, like a circular linked list, with reference counting. But anyway, they're all three kind of the three like main approaches to automatic memory management in compiled languages. All right, big aside on that. So if you're interested in this, let me know. I can point you to lots and lots of resources, or just Google this stuff about like, the Rust and Go and Swift. All very cool languages designed by, awesome people, just like champions in the programming languages world. All very good stuff. Okay, so that's pointers and arrays and memory management, and some of the kind of cool aspects of programming language design that have come out in really the last decade or two. So now I'd like to go over, actually show some of this pointer manipulation stuff happening in GDB, what the state of the machine looks like when we do this pointer arithmetic stuff, and also give you some hints about how to generate code that works with pointers. Okay, let's see. So I'll give you a second. So let me set up GDB, and I'll give you a second to just take a look at this Simple C program. It's very similar to what we saw in the slides. But let me get this ready to go. Make sure this is right. Okay. So questions on this code snippet? So somebody asked, okay, so one other question about pointers. Somebody asked, can you do pointer arithmetic to get parts of a struct? And yeah, just like arrays, structs are also accessed through offsets to a pointer. So structs are also just pointers. And the compiler, instead of doing pointer arithmetic by the index number, it automatically computes the size of each field and uses pointer arithmetic to get the parts of a struct. So they work the same way as an array, except you name the entries and give them types to have, give them sizes. And that's how the compiler computes the offsets. So structs, same way, same idea. Yeah, that's people. Yeah, pretty cool, right? This is it's nice to see, unbox the open up how open the hood on C and see how this works. So somebody asked the arrow. The arrow does a dereference, then designate then a selection. So it's the equivalent to dereferencing and then doing dot to access the field. So it dereferences first and then does dot. That's arrow. It's just so common that the designers made a its own construct for that, its own symbol. All right, let's go through this example program in Simple C. Just like before, we allocate a integer variable x, we allocate a pointer to an integer y, and we allocate a variable z. We assign 10 to x, get the address of x, so now y holds an address. And then we dereference y and assign it to 7. So now what's the value of x at this point? Just make sure everybody's on the same page. What's the value of x at this point after we, okay, good, it's 7. So y is an alias to x's value. And then we assign z to the dereferenced value of y, which also is 7. When we return x, since everybody already knew that x is 7, we get the value 7. Questions on this program at all? Makes sense? Okay, good. Good. All right, so let's take a look at the assembly code. It's a bit much, but let's go through it. Let's go through it carefully here. Yeah, it's a little much, but let's I put these comments in there so you can see the individual pieces of the code generator that produce that code. And so these, I think, should also be on, I'll show you the project for description before the end of class. Okay, so let's break this down. Yeah, you should be given all the assembly examples as well, so you can do hand comparison. We won't compare the assembly code, we'll just compare the output, but the TA should also give you the correct assembly code output. Okay, so let's skip over the prologue to the function, the parameters. And now here's the body of the function. The first thing that happens is we generate code for the right-hand side of the assignment. This is the familiar integer expression that we saw before. This is the code that does the assignment to X. So as we hopefully, I think we saw a week or two ago, variable assignments are just moving the contents of the value of the expression into the stack frame. And note here that effectively, this is also memory indirect addressing, by the way. But in our programming language, that's what the compiler is using. But in our programming language, we don't treat this as a memory address. We just treat it as a variable bound to an offset. Okay, so here is the code that gets X's address. So as you correctly pointed out, the address of X is just the base pointer minus the offset into the stack frame. So we already know the offset because we have it computed in the symbol table, the offset table that the code generator maintains. So you've already implemented the variable XS, then getting the offset to get the address, for a reference is using the same functionality. So we start with the base pointer, RBP, save that in a register, and then just subtract the offset from that address. So this is effectively doing what this indirect access to the address does, where we subtract 8 from RBP. But here, we don't want to access that memory. We want to compute the actual address of it. So we just use pointer arithmetic. This is equivalent to just saying, give me the address of the stack pointer or the base pointer, and then subtract 8 from it. Just pointer arithmetic here, but in assembly, which makes it, I know it makes it a little more confusing, but it's just doing effectively pointer arithmetic on the base pointer itself. Making sense so far? Okay, that's good. I know. Yeah, this is. I know this is a little. This is definitely complicated. But yeah, you can go back and watch and pause to fully grok this. So somebody asked an interesting question here. Where's the code that declares the variables? So that's a good question. Does anyone know the answer to this? So some people are saying it's subtracting from the stack pointer. Yeah, so in a sense, declarations don't have corresponding code in a sense. Okay, so let's take the questions one at a time. So in a sense, code declarations are not truly machine code. They're not operations. They're really just kind of hints to the compiler or instructions to the compiler itself to say, I want to use this symbol. Can you please allocate space for this for me at runtime in memory? And then when I use those in operations, then those will correspond to assembly instructions. So if we look at, let's see, I can't remember if I gave what I gave here. decal list. So you'll notice, yeah, so I didn't give it to you in class, but decal list loops over all the declarations and just computes the offset. So the only thing that the compiler needs to do when there are declarations is make space on the stack. So for those who said that this is effectively the code that's generated for declarations, that's basically right. What the compiler ends up doing is making space on the stack for it. So the question is, why is it 40 bytes? And yeah, so some student already answered this. They already figured it out, that we have 3 local variables. But then I built in argv and argc, which is another 2 variables, which is why, yeah, which is exactly why there's 40 bytes at the beginning of this, at the end of this stack frame for all the local variables, for the parameters. And so when you implement code generation for functions, you'll also allocate space for the one parameter that our simplified version of Simple-C has, where you have to have one parameter. And then you'll use code gen decal list to update the offset table to compute. And the offset table, I've built the offset table so it automatically computes the offset of the stack for you. But look at the project 3 instructions, which should give you enough information to do that. So good. You answered your own question, which is a good summary. So as the student says, we kind of just save space for the memory, but there isn't really an instruction that corresponds to a declaration. And someone else points out each stack frame's offset that corresponds to each memory address. So good, very, very good. Yeah, the declarations don't really correspond to instructions. They're really kind of instructions for the compiler. And there, as another kind of tangent, there's a whole nother area of research where you provide more annotations to the language, not that translate to code, but actually provide more guarantees about how the symbols are used. For instance, a type guarantee is that the compiler will only use, say, an integer as a 16-bit type. And for a strongly checked language, it will actually prevent you from using it, say, in pointer arithmetic like Simple-C does, or using it to add to a struct, which C will do unless you do some explicit typecasting to get pointer arithmetic to work. But you can also provide annotations that say, well, I want this to be an X, an integer that is always positive or is never a null pointer. And then program analysis tools can go through and try to ensure that that will never happen at those guarantees are held at runtime. Yeah, so somebody points out that the negatives are confusing. Yeah, negatives are very confusing. You just have to remember that the stack grows downward in memory. And the more you look at decompiled code, or I'm sorry, the more you look at disassembled code or other disassembled code from the compiler, the more you'll just see, well, okay, these are negative offsets from the base pointer. That's obviously a variable access. And you just kind of get used to it. But it's an artifact of how the system is designed, where running programs have a heap starting from 0 and a stack starting from the high memory address. You just get used to it. And I even made a mistake when I was writing this. I was like forgetting when I was writing that little tricky example that got the offset in the from the address, or where was it? Yeah, I made a little mistake when I was confusing addition and subtraction in a memory address. I can't remember what it was, but I was making that mistake too. Okay, so let's go. Let me go through the rest of this, and then we'll walk through it in GDB, and then I'll go over project 3 and 4 again, and that'll be end of class. Okay, so where were we? So we just computed the address of X using the compiler actually emitted assembly code that does the pointer arithmetic. We took the base pointer's address and subtracted 8 from it, because we know that the offset of X is -8 from the base pointer. As any expression does, it saves the result. And now that we're in the assignment, we get the right-hand side of the assignment. We pop it off the stack just like we do with expressions. And so what's the next thing here? Oh, it's here, sorry. So this is the left-hand side of the assignment, where we take whatever the expression value was, in this case, it's the address of X, and we set it to be the value of y. So we're not dereferencing y, we're setting it to be the actual value of y. And remember, y is a pointer, so it holds memory addresses. And this just stores whatever the expression on the right-hand side was, which we got by popping RAX. And it stores it in the stack frame for y. So we're not dereferencing the pointer here, we're setting the actual pointer value. Okay, now in this case, ooh, I feel like something is missing here. Oh, okay. Sorry, this is confusing. It's confusing for me as well, but you just have to work through very, very slowly. Okay, so this is the code for assigning the dereference to y. So it first, generates the code for the left-hand side. So the code for the left-hand side computes the address that the dereference operation is using. In this case, it gets the value of y, which we get from the stack frame entry for y. Save it to the stack because it's an expression. So now we have the address of y stored on the stack. Then we get the value of the right-hand side. So we've seen that before. We just move y onto the move 7 onto the stack. And just like a binary expression, except in this case it's an assignment expression, we get those two values from the stack. So we get the right-hand side value and the left-hand side value. The right-hand side value is, in this case, 7. The left-hand side value is a memory address. And here, this is where we actually do the memory indirect addressing that implements this assignment to a dereference. So I know I'm going through this a little bit confusingly, but if you walk through this yourself, it should make sense. So basically, this is what the assignment statement does. It pops the value on the right-hand side, pops the value on the left-hand side, and then just does a pointer indirect move, a memory indirect move in order to do that dereference assignment. So it's very much like the regular assignment. The regular assignment, all it has to do is pick out the right-hand side from the stack. The left-hand side we know because we can compute the offset from the base pointer. So this is what a regular assignment looks like. An assignment that uses a dereference looks like this. It has to first generate code for the right-hand side and the left-hand side, pop both those values, and then use a memory indirect move in order to implement that pointer assignment. Questions on this? You must have questions on this because to me that sounded confusing when I explained it. So what questions do you have on this? Does this make sense at all? And did I get lucky and actually explain this clearly? Or what questions do you have on this? Okay, yeah, not so simple. Okay, let me see if let me go through it one more time. Let me go through the project description. Maybe that will be a little clearer. Yeah, it's definitely going to be a rewatch and stepping through on your own. It's a little tough for me to explain this, especially since there's two kinds of assignments in that you have to generate code for. Okay, so depending on whether your left-hand side is a dereference operator or just an identifier, you're either going to generate an assignment in one of two ways. The first way is just you move whatever the expression is into the offset into the base pointer. So that's the regular assignment that we talked about a week or two ago. For assignments to a dereferenced pointer, the assignment statement is going to look a little bit different. It's almost like a binary expression in this sense. So the first thing we do is we recursively generate code for the left-hand side expression. That's y. Y is the left-hand side of the expression in our example. We recursively generate code for the right-hand side. And then once we're back in our assignment statement, we pop the results of the right-hand side and the left-hand side, and then use a pointer indirect addressing to update the value of the address pointed to by y. You know what, actually, I think showing this like we showed binary expression might actually be even better. So let's take our assignment here, y equals 7. And instead of a binary expression, it's an assignment statement. And in C, assignments are actually expressions. They're not even statements. They are actually expressions. So this assignment statement on the left-hand side has a unary expression, and that unary expression contains one ident expression, which is y. The right-hand side of this assignment statement has an int expression, and that int expression has 7 as its child. Is everyone with me on this so far? So what the parse tree looks like for star y equals 7. All right, okay, great. So the first thing we do is, just like binary expression, we first need to know the values that we get on each side of these expressions. In some sense, the assignment statement needs to first check that we have a unary expression and get whatever this expression is. Because this could be an arithmetic expression to do pointer arithmetic. We don't care what it is. We just want to find what this, the value of this expression is. Okay, so let me get my notes here to make sure that I am giving you the actual, giving you the actual assembly code for this. Where is it? I need assignment. Sorry, I'm just trying to get my notes here so I do not steer you the wrong way. Okay, so the assignment expression has to actually check whether the left-hand side is a unary expression or not. So if it's not a unary expression, so it's either going to be an ident expression or a unary expression. Otherwise, the assignment expression, it's not a valid assignment expression. There's only a limited two types of expressions that we support on the left-hand side. These are those that correspond to L values in the language. So in this case, when we deal with pointers, if we find that the left-hand side of the assignment is a unary expression with a dereference operator, then we know that we need to compute that address and then use memory indirect addressing to update the value. If it's any other unary expression, it's an error. If it's anything other than an ident expression or a unary expression with a dereference, then it's an error. simple C and C don't support other kinds of expressions on the left side of an expression. Okay, with me so far on that? So for project 4, we check whether it's a unary expression that has a dereference operator. And then we need to recursively generate code for this expression, whatever it is. The type checker could catch that, but I didn't specify it that way. So the compiler can just, the code generator can fail for that. You don't have to put, you're going to have to add extra checks for this. I don't think the type checker checks it. But we're not going to give you tricky examples like this anyway. Okay, so we need to compute whatever this is. We don't care that it's y, we don't care that it's y plus 1, because remember, y holds a memory address. So as long as we compute this expression, we're going to end up with a memory address. And whatever point arithmetic we're going to do on it, that's just going to be handled by the expression code generation. So what's going to happen here is this ident expression is going to generate code to the normal code for handling getting values from variables, just like any other variable access. And as every expression does in our scheme, the last thing it does is pushes the value into RAX. We do the same thing for the right side, just like binary expression. And in this case, we've seen this already. So it's going to move 7 into RAX and then push RAX. Okay, so now we are back up here inside of our assignment expression. Just like a binary expression, it's going to pop both the left and right hand values off of the stack. I'm just going to happen to choose RAX for the right hand side and RBX for the left hand side. The choice of registers doesn't actually matter as long as we make sure the move instructions are right. Okay, and now, so at this point in the program, what does RAX hold? If we're running this program, what does RAX hold at this point during the execution of the program? So recall that we ran the left-hand side first and then the right-hand side. So the stack, 7, good. So the left-hand side went first, so the memory address is pushed onto the stack, and then the right-hand side goes next. 7 is pushed onto the stack. We pop 7 off of the stack, and then we pop the address off of the stack into RAX and RBX. With me so far on this? So it's just like binary expression, where we want to compute the values of the left and right hand side and get them into memory and get them into our registers. All right. So now that this is the right side, this is the left side. Recall that the left-hand side, because we're using a pointer dereference, the right-hand side is going to be treated as a memory address. Whatever it computes in that expression, we don't care what it computes. The fact that we use a memory dereference, that star, that tells us that we want to treat that as a memory address. So the way we treat it as a memory address and store the value of the right-hand side at the memory address pointed to by the left-hand side is we use this memory indirect addressing. So we take, and if you remember from the slides, we use this subtle notational difference in the assembly level, which makes all the difference for pointers. Instead of moving to, like in this case, we moved to an offset on the stack frame. Instead, we move to whatever the address on the left-hand side, what we computed on the left-hand side. Does this make a little more sense from what I explained before? Okay, great. Okay, thank God. Okay, thank God that works better. So to kind of do the same thing I did before with the expression, the code generator, because it's recursive, because it's bottom up, because the code generator works, oh, come on, works in this bottom up fashion, it's going to generate code for the left-hand side first. Then it's going to generate code for the right-hand side. And once the code generation is done for the left and right children, it's we're going to be back inside of the code generator for the assignment expression. If this will please cooperate with me. It's going to finally generate the rest of the code for, what am I doing? It's going to finally generate code for the rest of the assignment expression. And because of that contract that we made between the code generators for expressions, all we have to do is pop the left and right values from the stack. And because we don't care what the left-hand side was, we just know, because the developer told us this is a star, treat it as an address, we just generate the memory indirect addressing version of that assignment. All right. Questions on this so far? I think this is much clearer, which is great. I think this is much clearer. Questions? Okay, yeah, definitely rewatch. This stuff is very, very tedious and low-level details of the machine. And it's extremely hard to not only understand how this works from the assembly point of view, but to generate code that does it and does it correctly. Very, very hard to do. If you can get through this, push yourself through this, don't be scared, push yourself through this, you will be a better programmer in all aspects. You'll understand the back end, the low-level machine. You'll understand how programming languages work and be able to use your programming language more effectively. And through the difficulty of these algorithms, you'll just understand how to implement algorithms better. So somebody's asking, are we going to push it? Oh, push the resulting value. That's interesting. So you don't have to do a push at the end of this, because at least in our language, the assignment statement is not an expression, it's a statement. So once we're done with this, there's no other constructs that rely on the result of this computation. Once we've done the assignment, we're done. C is different. The assignment expression does actually return yet another L value so that you can chain together multiple assignments, but it makes things more complicated. So we're not doing that in this language. Once it's a statement in simple C, not an expression. Okay, so that's pretty rough. This is definitely a tricky exercise. I've tried to give you very explicit instructions in the project description. Come to office hours, ask questions next time in class, and we will try to get through this. I may extend project 4 as needed, but I don't want to extend it yet because I really want you to start focusing on this. You have tons of exams and other projects, I'm sure. So let's try to get this done soon while this is kind of fresh in your mind. It's really not that much coding. It's just tricky to get it right. So the code you'll have, you'll be very surprised at how little code you have to write to get this compiler done. It's really all about the reasoning to get it right. That's one of the, another main thing that I want to get across in this class is that put the time in to get the reasoning right, and then your code is tiny and small and efficient and easy to verify the correctness of it. Yeah, project 4 is this is true for project 4. The code is really pretty small after I give you the template. Project 4 is kind of a continuation of project 3. I just divided up the code generation into 2 halves. I'm not going to give you project 3, the binary for it, because we'll just try to test only part of project 4. You're still going to have to do assignment statement to some degree. You'll have to do part of the assignment statement for project 4, part of it for project 3, because assignments in project 3 are updating the stack frame, whereas assignments in project 4 are updating the pointer. Yeah, so somebody asked about grading. or grading it by checking the return value of your function. We're not going to match the assembly output. So you don't have to get white space right, or if you want to do register allocation better or use different registers, totally fine. Should not affect your grade. It's all based on the return value. Okay, so I'm over by 10 minutes. Office hours should be starting soon, but the project descriptions are online. For project 4, I have the pointer part put in there. We're going to go over, I mean, project 4 is not even, you don't even have to work on it yet. Project 3 is, assigned basically starting last week, and you have 3 weeks to do it. Project 4 starts at that point. And yeah, so good luck. I know this is challenging, but I hope I'm trying to give you all the tools so that you can successfully do this compiler. It's not that much code. It's just the reasoning through it. You have to first sit down, reason through it, write your own test cases. Don't just try to write code, run it, and debug. That's going to be really, really, really hard to do with a hard program. And then this will hopefully give you better habits when you code simpler projects. All right, everybody, I'm going to move to office hours. Take care. Have a good weekend, and good luck. Bye, everybody.